Alright guys, so we're going to talk about double integrals. We're going to try to go slowly and set them up very carefully. So let's start just with a region. I'm going to do y equals x squared and then y equals square root of x. So this one right here is going to be y equals square root of x, and this is going to be y equals x squared. Let's start with that region, and the region in between the two curves right there. So if you want to determine what the region is, firstly, you're going to find your intersection points. So you're going to set them equal to each other. So in this case, x squared is going to be equal to the square root of x. You square both sides. You get that. Now, don't divide by x because you would be eliminating 1, 0. Instead, you subtract the x on both sides and factor. This gives me an x equals to 0, which we could see from the graph. And another one, this one gives me an x equals to 1, and another two complex roots, but we don't care about. And that will be, those will be our intersection points. So now, what is our idea? We're going to set up an integral to or a double integral to calculate the area of this region in two different ways. So we're going to start just computing areas. And so the area of the region is going to be the integral, double integral over the region of the differential of area. So meaning that you're going to grab a little differential. Well, you're going to partition this into, say, a grid, if you will. And you're going to grab your differential of area. And you're going to be adding those differentials of area across the entire region. That's going to give you the area of the region itself. So what I want to do is I'm going to set it up in two different ways, because the differential of area could be dx dy or dy dx. We're going to do polar coordinates later, but at the moment for rectangular coordinates would be dy dx or dx dy. So whichever I choose is going to change the order of or the boundaries of my region. So let's go ahead and look at the first one. Let's do dx dy. So if I do a dx dy for my differential of area, what will happen is I'm going to be integrating first with respect to x, and then lost my marker, sorry. Then I'm going to be integrating with respect to y. So what do I need these boundaries to be? Well, whenever I integrate with respect to x, that's fine. I take care of the x's, but the second integral should be with respect to y. So here I'm going to need functions of y. Otherwise, you're going to end up with something you're going to integrate. Who knows what that will be? Because you're going to end up with a y that you never, or an x that you never cancel if you don't get the right endpoints. And then I'm going to go from a to b. Now, if I wanted to integrate in the opposite order, and I wanted to do dy dx, now notice that the second time I'm integrating, I want to have something that depends on x. So here I'm going to call them a different name. Perhaps h of x, I was going to say y, but it's x, and L, if you will, of x. And then here you'll go from some other numerical values, c to d. So that's going to be the form that those integrals will take. So how do I find those things? Well, you already know what your functions are, and we found the numbers. By the way, I have the numbers for dx. So the one I have is the second one. So if I want to do the second one, I can do automatically with the way I have it. And the way you would do it is this. Somebody in a previous video told me not to say and and all that. And I'm working really hard, but I already caught myself saying it one time. But it's terrible because I realize now how many times I say those words now. Anyways, I'll try. I promise. So that endpoint right here, if you plug x equals to 1 into your y, gives you y equals to 1. So for the x now, you would be going from 0 to 1 in this direction. Now, remember, when I have a dy first, I need functions of x. Well, I do have those in this case. The lower function, you're always going to go bottom to top. So from the bottom, you're going to have x squared. In the top, you're going to have the square root of x, because in this case, the square root of x goes above. And now for my x's, I want to go from 0 to 1. So that is one way you could set it up. That is this one right here. However, if I want to set the integral in the opposite order, what I want to do is then have functions of y. For that matter, then I would have to solve this function here, or this equation rather, and write x as the square root of y. And now this one over here, it's kind of funny because the integral will be exactly the same, but whatever. In this case, x would be the y squared. So I picked my problem so well because the integral will look exactly the same, just replacing x and y. Anyways, so I'm going to be going from the bottom function, which is the square root of y. Bottom function, square root of y, yes. To the top function, oh. Well, that's how you do not do it. You're going to go from left to right because we're doing, you're fixing a y. And now you're going to do your functions in terms of y. What each function is going to give you is an x coordinate. So you're going left to right now. So the one on the left is going to be y squared, unlike what I wrote here. And then on the right-hand side, you're going to have this function, which is going to be square root of y. And you're going to be going now in the x direction from 0 to 1. In the y direction, I said, from 0 to 1. So dx dy. So it looks exactly the same for it because the problem I chose is so symmetric, where these functions are inverses of one another on the interval between 0 and infinity. So I chose one example that actually looks the same. It doesn't have to be. In fact, normally it will not be the case. However, I'm going to do another example, and we're going to try to then, with that example, introduce the idea of polar coordinates. I want to change into polar coordinates. However, what happens if the function is not just 1 times the dA? So what would that represent? So let me go ahead and try to draw this same region, and we're going to just come up with any function, and we'll talk about that. All right, so let's go ahead and draw this same region, but now we're going to draw it in 3D. And I will give my typical warning or disclaimer that my drawings in 3D are fabulous, to not say anything else. So you're going to have that region in your xy plane. So we're in the xy plane here. Okay? And let's say that we have another function, and I was supposed to think about this function, but I didn't. So I'm going to go ahead and write just my favorite function, which is going to be z equals 1 minus, actually I'm going to do 2. 2 minus x squared minus y squared. And why would I do that is because that graph, and I'm going to try to be judicious with the colors, is going to look somewhat like, I'll be careful, a little bit this way. It's going to look like this. It's going to be a paraboloid that opens down. Now, why did I superimpose that on that region? Is because I'm going to look at what happens when you integrate this function. So if you were to integrate this function over this region. So now that we have the endpoints for our intervals for a region, we can rewrite it. And if we put this function z, in which order did I write it? dx dy. So what would that integral represent? So if I just grab this function, or this integral, which by the way would just be the integral of my function, let's call it, I guess I'll write it as z over dA over a, over the region R rather, what that would represent would be the volume of the curve above that region. So what would that look like? What color do I pick? So it's going to be a cutout of this function that is kind of going to look like, if you go up here, there, and then all the way up, you go up there and hit the graph, go up vertically, then you would have a wedge in 3D that would kind of be a section. Oh, that doesn't look anything like it, but you'd be cutting out a section of this curve above the region, and the volume would be given by this integral right here. Doesn't look like what I wanted. When you integrate the function over the differential of area over a region, so you're getting the volume of the figure above that region and under that curve.